Welcome, everyone. My name is Michelle Branzaleski. I'm the Global Marketing Manager here at Control Station. I realize it is the top of the hour, but I do see a lot of people still signing on. So we're just going to give it another minute or two before we get the presentation going. Thank you for your patience. All right, it looks like we have the majority of people on. So let's start the presentation. Again, my name is Michelle Branzaleski. I'm the Global Marketing Manager here at Control Station. I'd like to thank you for the privilege of your time today. We know everyone is busy, but we put together a fantastic webinar, and it's going to be a panel discussion. It's called The Habits of a Systems Thinker, and we have 3 different perspectives that I would like to share with you. If you could go to the next slide, please. So with us today, we have Dr. Bob Rice, who's the VP of Engineering here at Control Station. Good morning, Bob.
Good morning.
Also with us today, we have Damian Monroe, who is the Integrator Director for the EU, Middle East, and Asia. Good morning, Damian.
Good morning, good afternoon, and good evening, I suppose. I'm coming from Europe, so it's afternoon here, but hello all.
And also with us, we have a Senior Project Engineer, Vince Haig. Vince, good morning.
Morning.
All right, gentlemen, thank you. So if we can go on to the next slide. All right, I'm just going to cover a few housekeeping things on a little bit on who Control Station is. So we have been partnering with our customers since 1988, so well over 30 years. We are proud to partner with 1 out of 2 manufacturers listed in the Fortune 500. We have offices in the United States as well as Ireland, as you met, Damien, and we are successfully deployed solutions in support at facilities in over 70 countries, and it's still growing. Next slide, please. Today's agenda, what is the typical situation at a plant? We'll cover that. Then we're going to cover what the habits of system thinkers are. We'll have our open discussion, we'll do a summary, and at the end, we will take questions and answers. You will see on your toolbar, there's a bar called questions. On the right-hand side, if you click open pane, you can open that up and type in your questions. So with that, I would like to hand things over to Bob.
Excellent. Thank you very much. So I would like to go ahead and just kind of start this off and talk through about kind of today's situation, right? With the advent of cloud-based systems and enhanced data access, it's kind of fundamentally reshaped the landscape of process control and industrial operations, right? Real-time monitoring is now the norm, right? With data from various instrumentation being transmitted to multiple platforms for immediate analytics, whether it's local, whether it's cloud, whether it's in data center, whether it's in corporate. And this shift has not only enabled engineers and operators to monitor and react from processes from virtually anywhere in the world, it has also paved the way for advanced machine learning, AI integration, advanced analytics, leading to highly adaptive and optimized control strategies. It's given us an opportunity to take a step back and look at the bigger picture, right? Moreover, these modern IT environments offer much more scalability and flexibility to grow along with the operations. As your processes get more complex, your systems, your IT infrastructure, everything can grow along with it. So all of this collaboration has been enhanced with teams from different locations accessing unified data, driving those kind of data-centric decision-making processes. And having that thought process, all that big data, really allows you to take a much bigger picture when you're thinking about your process. You're not just looking at optimizing, oh, I'm going to go tune this one loop. You're going to start looking at optimizing a process, optimizing a unit operation, your plant, your entire fleet, optimizing everything. And it all starts with looking at, the individual controllers, the individual applications, but you got to see that kind of big picture. Now, of course, you can't really have this discussion without saying, there's always challenges. All this increased connectivity, the data flow, you do have to always keep in mind the cybersecurity vulnerabilities, make sure you've got robust protective measures, and so forth, right? And, cloud platforms, centralized data systems offer a lot of cost efficiencies by reducing the need for traditional independent infrastructure. So you can kind of start to share resources, which really allows that kind of economies of scale to make sense, right? Instead of having to put in, 60 different individual systems, you can have one large system and you can really start to capitalize on all of this digital transformation. And there is a lot of potential and challenges that are associated with this. And so how do you approach these types of applications? Well, kind of taking it down to the habits of a system thinker, right? You have to think about what you're trying to do. Process control is that kind of fundamental element in our space that's used to maintain, regulate, and optimize operations. Applications such as chemical plants, refining, pulp mills, different manufacturing units, they all understand this kind of intricate web of interconnected processes is vital, right? It's not these individual islands of automation. You have to understand all of the complexity. And these operations, they're inherently dynamic, with changes in one component influencing multiple other systems. So to navigate this complexity, in this field, we have to adopt kind of that systematic approach. And that emphasizes these habits to have a deep understanding of the system dynamics and the interdependencies of the system, right? Drawing on these habits allows us to offer insights on how to best ensure that your processes run smoothly, efficiently, safely in the face of these unforeseen disturbances and changing operational conditions, right? In a little while, we're going to have kind of an open discussion to kind of talk through these habits of a system thinker to really help you understand, how do you examine the local applications? How do you start to anticipate or envision opportunities? How do you consider what's going on? How do you validate it? How do you recognize it? How do you put in place these processes to be able to start taking your view from that narrow focus to something much more wider to understand how does the performance of one little application, how can that kind of expand out and get to real dollars and real optimization for individual plants as well as to fleets and to areas and so forth. So I know Michelle wanted to start off a little bit here with a poll to talk about some of the ideas and concepts. So Michelle, I'll let you take this part.
Thanks, Bob. All right, I'm going to launch a poll and you should see it on your screen in a minute or two. Okay, so it says, what do you consider an important habit of a systems thinker? To examine, anticipate, envision, validate, or consider and recognize? So select as many as you think apply, and I will leave it open for a few minutes. In the meantime, I would like to do a plug for our next webinar, which is October 17th. You will get an email invite from me. Otherwise, please feel free to go sign up online on our website. And this is hitting home to a lot of companies. It's going to be about sustainability. And with better controls, how do you improve sustainability? So look forward to that one. And again, that is October 17th. Okay, I see a lot of people. So everyone, I think, is voted. I'll wait a second or two, and I'm going to close it, and I'll share the results. So it's pretty even across the board. Over 50% think all of them apply. All right, so I will hide this, and I would like to hand it back over to Bob.
Excellent. Thank you, Michelle. So what we'd like to do now is to kind of open up this discussion to our panel. And as Michelle introduced everybody earlier, myself, Bob Rice, Damien, and Vince are kind of going to talk through the different habits of a system thinker and the different things to kind of focus on as you're approaching this problem. And we'll start at the beginning here, which is the examine, right? We have to examine the process. We have to observe how the elements in our system change over time, right? Applications change. And so we need to be able to understand what's going on with the process. We need to be able to help identify KPIs. We need to help identify the individual components that we care about, right? So if we're looking at, for instance, the temperature of a reactor, right? And so the operators may monitor this temperature of a reactor over time. If that temperature starts to rise, that could be a problem, right? It could be a deviation from a desired condition, right? And so this habit's really designed to monitor those variables. So you have to identify those variables, monitor those KPIs, things like average error or distance from set point or output travel or oscillation detection. You have to examine and identify what are the things that you care about and what are those KPIs that are actually relevant to your process. Vince, as the product manager for Plan ASP and some of our other solutions here at Control Station, how do you kind of walk into this examine section? What are the techniques that you're using on the development side?
Yeah, so it's interesting from the product side. We don't focus much on the physical aspect. We actually we focus a lot on the um, requirements of the system. So if you think back to when we first started developing software, it was really limited to processing power. How fast can you compute um, some kind of mathematical operation per millisecond or whatever. And as time uh, goes by, Moore's law, more microprocessing power, more chips on a system on a silicon wafer. Um, we have this capability to do more computations to handle more processing. And on the software side, that's good for us because we can use those resources on the physical layer to do more computations, to pull more data um, from different systems. Just speaking on the PID perspective, right? When you were tuning back in the 90s, you had your really old your Slick 500s and whatnot from the Rockwell side that just aren't as powerful as the microprocessors that they have today, like the control logics or micro logics. Again, speaking from Rockwell systems, um, and that's just over the past 20, 30 years. That's how um, hardware and software has changed. So on the product side, we have to sort of try and keep up with that, understand that, okay, systems are much more robust these days. They can handle and do more computations, but at the same time, you're adding complexity because now you have different communication protocols, which can be good or bad. Um, just again, thinking back to the 90s, all you had was like OPC DA version 1.0, right? Now you have OPC UA, which you can connect over IP, which is internet. You have different systems connecting to different databases. You have Pi historians. You have prophecy historians, just different backends. So as hardware develops, software has to develop also to try and keep up with that. So, thinking from the examine perspective, how systems change over time, um, understanding that we have to keep up with the changes in that aspect. Damien, you work more on the integration side. Can you go
Yeah,
ahead and speak on that?
it's interesting from your both perspectives on it's somewhat virtual. I'm quite practical and applied at the cold face is the wrong word, but with standing in the control room, considering how the system is or isn't performing, I ask myself one deep and meaningful question. And anytime I turn up in front of a system, why am I here? You know, it's the what has brought me to stand here and look at this particular process. Is it a problem in the process? What's it not doing? Why is it not doing it? And you have to kind of broaden yourself out around that to go, okay, so where did this problem get reported? Is it operations? Is it process? You know, is there an alarms getting tripped on lack of control, or something is driving that? And it's really is to analyze that or examine that information and start from there. Answer that question, then it will give you another question. Operations reported, they cannot control this process. It's oscillating. It's this, that. Okay, so when did it happen? Where did it trigger from? Was there something? Yes, we did a calibration on that system last week, and since then we've never been able to control it. It's gone. You know, there can be a specific event, or we changed a supplier of a material. We increased the throughput. There's always going to be a tie to it that you have to work back through, and you have to find that information from as many sources, or you have to look for it from as many sources as possible. Yes, it's in the analytics. It's in the historian trend. I love looking at a trend of a process for a week, a month, and a year, because you can see it. You know, is it still exhibiting the same problems, or is there specific sections of that data that are screaming a problem, whereas there's other sections that are not. You know, so it's using that why am I here question, talking to all of these people to examine that. You do have to broaden your search. We all have to put our hand up, and we're not an expert in everything. We've got skill sets, but you have to pull in from ops and go, you know, a worst thing I hate hearing from ops people, sure, it's always been like that. That's a problem, you know, because they're only noticing it now, or management are perhaps only noticing, but the ops go, yeah, that's always ran like that, you know, and they go, okay, that's actually quite positive, because you then know that this is normal, and then you can decide, well, how do we improve this? What's required to improve it? You know, it's taking that step and moving into this next section of anticipate, where you have to start to build all that information and get that knowledge together. And then you start to say, well, how does it relate to my process? Where does this system sit in that process? Is it front of line, end of line, midstream? You know, why is it not performing? Is it something that's specific to this production line? Or, well, we've 10 production lines doing this, or 10 air handlers, but this particular air handler or this particular process is not performing. Or every time period, whatever that may be, it starts to drift. It starts to radically oscillate. Some industries call them dog tools. They're a piece of plant that is always the struggling, and you know, the reasons for that struggle can be varied, but typically it's around limitations on the process. I've seen 10 air handlers in a row, and the one at the end of the chilled water line suffers with quality of delivery or consistency of delivery, which can cause it just to exhibit poor performance, you know, at specific time of high load, etc. You know, it's something that is always kind of, you need to find that reason as to why is this process, and then start to see, is that cause and effect? Does that, what I have discovered, can I correlate that or relate that to the data I'm seeing, or to there's an entry log in the maintenance log called to air handler 10, and you look down through the list and it's been visited every week on a Monday morning after a problematic weekend, you know, and they go, okay, so there's something repeatable on this process and stuff. So Bob, do you want to take that from there again, going back into the analytics of that? So where do you see that coming?
You know, anticipate to me is always about trying to identify that kind of circular nature of cause and effect. Right. And there was a comment that Damien had made earlier that's, you know, hey, you know, that this loop's always been this way. Right. And you know, that always gets under my skin, because when I see things that are not behaving well, and they've always not been behaving well, you know, why is that? And a lot of times it's because there's this thought process that, oh, well, this loop doesn't matter. This level controller can swing all at once. It doesn't make any difference. Or this temperature or this flow, it's way over here in this side of the plant that has no, interdependencies. Well, that's not always true. All of our plants are very interconnected, and they're not these individual islands of automation that live, separated from everything else, right? You have all of these relationships. You have these cyclings, these instabilities that can, propagate throughout the plant. And so being able to say, look, yes, okay, this one loop you may not think is critical, but when you start using some analytical tools like correlation analysis or spectrum analysis, and you can really start to say, well, yeah, I've got this swing over here, but now, hey, look, this entire unit actually has that same swing. And we've always wondered where that swing came from. Well, it came from that loop that nobody cared about, that was in the back corner of the plant that no one even thought about, right? Or even looking at things like feeds into your plant, right? When you've got fuel feeds or resource feeds that may come from an adjoining facility coming into it, you need to know what kind of impact those have. And so you got to start to understand and anticipate that, right? The examine is about identifying the individual number, KPI, or whatever it is, right? You've got a number. Now use that number to start to predict things, right? To anticipate what's happening with here. Where does this oscillation come from? What are the interactions, right? Start to use this in almost like a feedback loop to help you prove this out, right? When you're doing things like interaction analysis, it helps you prove why you should care about this loop, right? That's sadly so much of my job is showing customers, hey, yes, this is a terrible oscillation, it's bad. And they say, well, we don't care. Well, I have to prove to them that you do care. And using this kind of anticipate method of system thinking to use interaction analysis or correlation analysis to show where this kind of fits into the big picture is a really important role, right? Vince, when you're thinking about developing products, what are some of the ways that you've used this kind of anticipate thought process to building interaction tools or different software platforms?
Yeah, it's funny you mentioned that because software is all just one big clump of if-else statements, right? If this happens, then that will occur. So this cause and effect relationship boils down to the bits in a system. One is true, zero is false. So you have the binary nature of it all. Yeah, when we're developing tuning software or monitoring software, it's all of these. If this occurs, then what is going to happen? There was a time where we had some bugs in the software where it would calculate on the disabled bit. So when it reads the bit from the historian, the loop would be disabled, but it was still calculating, and you would still get a health value for it. And in that sense, it's misleading because when a loop is not running or is not enabled, you shouldn't really have calculations for it showing that, okay, this loop was not performing well because it's really off right now. And just understanding that, okay, when it's disabled, it's not supposed to give me a health value because it's showing that it's being worse than it typically is. Being able to know that, on the software side, know that, okay, it shouldn't be calculating at all, gives you a sort of a leg up on troubleshooting when customer calls and says, hey, I got this issue with your monitoring or your tuning, and it shows this value when it shouldn't. So being able to, on the first step, examine and understand the parts of a system, and then anticipating what the values should be coming out the other end. That sort of approach allows us to, number one, troubleshoot the issue and then fix it and issue our patches and our hotfix. But number two, it gives you a better understanding of the system as a whole, because now you can predict what the system is supposed to be doing, what the software is supposed to be doing, and even go into the physical aspects, right? Damien and Bob mentioned, when they're working with loops, if you add heat to a system, you expect that the temperature would increase in the final output. Well, if it doesn't increase, or if the temperature instead decreases, then where is the broken link in the system, right? Why isn't the heating effect working? Why isn't it the control that I've put into the system actually controlling. So finding these unintended consequences is part of anticipating. And this sort of leads us into the next part of systems thinking, which is putting it all together, right? Envisioning how all these small pieces start to come together. What is the big picture? So when you think about a system, it's different hardware and software working together, right? Different units, different instrumentation, different equipment. You have to get different teams working together. When we deploy, we don't just deploy to the process engineer. We deploy with the IT team, the database team. We work with maintenance because a system owner is responsible for their side of the entire system, right? So database owners maintain the database, make sure that it's backed up, that it's robust. The maintenance people are responsible for making sure that the valves and the pumps and whatnot are still within the desired lifespan, and that unintended shutdowns don't occur. So having this the ability to envision the big picture, to see how a piece of a system fits into the whole system as fits into the system as a whole, it's just one of the things that you have to be aware of when you start to examine and anticipate how the system functions. I'll hand it over to Damien to speak a bit more on the aspects of
Yeah,
envisioning.
that envision the process is you're starting to put stuff together. You're starting to make those connections and get correlations that ops is like that all the time. The trends, the historized data is showing that, the analytics is showing that. All of those components are starting to feed into this big picture question and go, yeah, this loop could never work because of X, Y, and Z. There was and so what we need to change the way in which we approach it. They're the good ones. They're the ones that you can go, okay, we can fix this. The things that just happen on a Friday, are if there's a definable value to that you go, yeah. And if you talk to the system owners, the guys that run that plant, they're going to go, yeah, well, every time we rotate that, it does this, and we try, and we've learned to do it this way. You can start to see actually another useful place to look for trends is in shifts in different operators of the plant. Yes, they all approach it the same way. They all have their methods of work, etc. But there can be subtle variations that can exhibit in decay in performance. And that will and you do have to be open to be looking at the very high level to see where those failures or deviations that come through that. It's something that the envisaging is to see all the information I've collated. Is it feeding into that, the validity of your model, the validity of your process? It's every one of those is a tick box so that you go, yeah, the oscillations that happen every 10 hours or every Friday is because of that boiler rotation, and etc. You do need to join the dots to it. But the data is where that really is coming about. Bob, I'm going to pull you in there, but that data lake, it's no longer a scary data lake because there's processes now to actually get that information out in usable forms. When I'm training, I always tell the attendees to look at the historized trend simply, because you get a really strong picture of how the process is working from that week, a month, or a year of trend that you can see very high level, not with an awful lot of detail, but because there's too much detail in it, but you get that impression of the process. Sorry, Bob, just go over to you on that with the data.
Yeah, I mean, with Envision, to me, it's always you're trying to understand the big picture, right? You've used Examine to identify the individual points, right? The individual KPIs, the individual loops, the pieces of your process. Anticipate kind of allows you to start to put the pieces together into the puzzle. Envision is when you get to take a step back and start to think about the big picture, right? when you're talking about all the units that are interconnected within your facility, you know, how can you start to envision how changes here can propagate and affect others as a whole, right? How do you ensure coordinated control between all these different systems? How can you take and look at the big picture, right? What's going on in my entire facility, not just in a particular area. So you can almost think of all these steps. Every time we go through one of these steps, we're taking a step further and further back to get a wider and wider view of what's going on. And so for me, Envision is always, you know, how do we get to the end game, right? How do we actually get to see, you know, values, KPIs, things that drive our entire facility, right? We're trying to understand the big picture, and we're trying to anticipate, we're trying to predict, we're using these KPIs to kind of understand the big picture. And it's funny, you know, we're going through these discussions, and there are 6 things that we're going to talk about, and we're halfway through, and a lot of people are probably thinking, yeah, we're probably done. We've envisioned it. We've seen the big picture. We've got to understand the KPIs. We're understanding the relationships. We're seeing the big picture. We've solved our problem, right? And it's funny. We're only halfway through this list, right? But Envision does allow you to see that big picture, to start to understand the relationships. And this next one, this next step, is the one that oddly is forgotten about. It's the validation, right? You've done all of this work. You've identified KPIs. You've understood. You built this understanding of relationships. You've built these models of your process. You understand where the oscillations come from. You've envisioned the big picture of, hey, if I drive these oscillations down, I can run the unit like this, and I can get a little bit more production through this. Now you got to take a step back and check your results and change actions, right? Validation is absolutely critical, right? Suppose you've created this new control algorithm to implement, to optimize fuel usage in a furnace, right? After implementation, you're going to want to make sure you validate its performance. If the fuel consumption doesn't decrease as anticipated, or if there are unintended side effects, you need to make adjustments. Don't be afraid to validate your process, because if it's not right, someone's going to find out eventually, right? So spend the time. You've done all of this work. Check your answers, right? Trust but verify. Make sure it's actually working the way you expect it to. Because if it's not, you need to circle back to the beginning, or whatever step that fails that validation, and start through. Make sure it works, right? Make sure the results correct, right? When I go and look at KPIs or results for doing loop analytics or loop analysis on an individual system, I always go and look at process data. I look at those long, short, and kind of medium-term trends that Damien was talking about, to kind of validate, do these KPIs and metrics that have predicted this behavior, did it work in the past, right? Did it, if I would have followed that KPI, would it have tracked that particular unit outage? Yes, that's great. Going forward, does it continue to hit that, or do we have to modify it? Right? There's always that kind of validation phase, right? Damien, to kind of hop right back to you, on your side, where do you see validation from an integration standpoint of doing these types of projects?
The couple of quotes I have, they'll come out here, but you do have to break a few eggs to make omelets. You're going to have to change. You're going to have to move something to confirm that it doesn't operate the way it did. So that's modeling. You're going to have to do a step test to find your tunings to make the new process. And it's negotiation. Your negotiation skills is part of system thinking, because you have to negotiate with everybody in that system to get information, but also to make changes. Operations go, no, you can't change that. That's that point. You can't move that set point. And I go, well, okay, but so where are the alarm limits? Where can I move? Where can I where can I play? So long as I don't hit that number high level or that number low level, can I operate inside in this zone? Because you can safely move around within that zone and confirm your assumptions, validate that what you've found and how it exhibits and how you then make changes, does it exhibit with a more stable system. You've moved the pH position because the titration was just too aggressive at that set point. We're looking to change the position where we operate. We're looking to change the amount of energy we're pushing into a system, because we don't need to have that much aggressiveness in a process. You do have to play, and you do have to negotiate to play, but there's always going to be an area in which you can safely operate, confirm that everything you've collected to date is now operational, and then you go, okay, now we can move on. The other rock solid rule you have is never make a change on a Friday afternoon, because you will be back in work on the Saturday or Sunday morning. You know, is because it's you have to be very careful on this planned implementation, that you're going to softly and subtly move in the direction you want to go, but don't all say changes. You are running a critical production process. Everybody's process is critical, so that but you have to just confirm that your logic to now and all the information you've fed into it is going to get you there. Vince, just jumping over to you there now with that on that baby steps, I suppose, is perhaps a way. How does that work into software?
Yeah, so validate is a big step. When we're thinking about, okay, now we have the picture, we've envisioned how all the different pieces interact with each other. Well, 100% there's going to be something wrong with a connection somewhere. And this is where really a lot of the instrumentation guys shine, the IT team also, right? Because you're connecting to all these different control systems. And at the same time, you have to make sure those layer one systems work. You have to make sure that the fiber or the Ethernet cable that's running from that control system to whatever computer or whatever workstation, it's going to actually be able to then transmit that data into the historian to be stored, and then the historian, the database has to query the historian for that information to store that information in the database, and then the calculation tool has to pull the information from both the historian and the database to run calculations and crunch the numbers and then validate that, okay, that floating point value that's all the way downstream or all the way upstream in the system is actually the correct value. And this is, again, from a systems perspective, you're talking about a controller that could be in the same plant or one that's in a different plant that's being pulled up to your, whether it's a cloud service or your analytics teams, corporate network, trying to look at the values, trying to try to track, being able to validate and understand that, okay, that value is where we left it or where it was known to be a good value. Again, when we troubleshoot systems, especially when it comes to monitoring and controls, it's always an issue with connection. Why isn't the OPC connection working? Why isn't the historian connection working? And it's, again, multiple multiple owners, right? Sometimes my user account doesn't actually have access to the historian, or my user account doesn't have SQL database access. So now you're just sending null values back, and the software just shows, okay, there's no values. When the operator or the process engineer is right there in front of the HMI, they're saying, look, I can see that it's 50 degrees or whatnot, but your system is showing that it's null. And that's where you sort of put the pieces together and say, okay, I know the big picture. I know how all of these networks interconnect with each other. How can I start to validate and test to make sure that the value coming from that controller, coming from the historian, is actually coming through correctly, right? It's you break it down into small pieces. Okay, we know that the network path travels from the controller to this computer right here, and we know that this computer is part of this domain and it connects to this system right here, and then that system right there is restricted to only these certain users. And again, IT and the instrumentation guys are really big when it comes to the validation aspect, because if those level one communication nodes don't work, then the whole system doesn't work, because you're not transmitting the correct data. To be able to do analysis, to be able to benchmark, to be able to trend the correct values and see how a system operates over time, you have to make sure that uh, um, those layer one devices and data is actually validated and is actually correct. And then, once you validate it and understand that, okay, the value is what it's supposed to be, now you can sort of try to build uh, secondary and tertiary consequences from it, right? So going sort of into the next item, which is considering, um, once you validate, consider now how the system operates both in the short term and the long term. Um, Back to a plant, when you're trying to control temperature, sure, you might add some cooling water, open the valve a bit, introduce some cooling into the system. But what does that do? Maybe in the short term, that cooling actually allows you to control the temperature uh, in that instant in time. But over the long term, your system, you're adding more wear and tear to the valve, or maybe um, you, the increased flow of the water might affect the way your instrumentation, your sensors, their lifespan, because now it's just being beaten by more pressure or whatnot. So you do have to consider that short term and long term. How would my changes affect what I'm trying to achieve? Because it's not just, okay, I see that the system needs some cooling, so let me introduce some cooling. I'm good now. I'm in control. It's yeah, in the short term it's good, but there are long-term unintended consequences. It's the same with software. You do a quick bug fix and you think that the bug's fixed, but then you introduce a bug somewhere else downstream in the system. Um, you have to consider, just because you fix one thing doesn't mean that the whole system is now operating the way that you
Absolutely,
intended it
Vince.
to be.
I totally agree with that, because and the bugs are not in the virtual world; they're also in the real world. You can implement something in with tuning, for example. If you say, I need to get more aggressive with my tuning, you're sacrificing long-term maintainability of equipment if you're making it work harder, if you're making it do more, for very little gain. I would um, my experience is 95% of PID loops out there are over aggressively controlled. They don't need to be that hard and running that fast. I have never is too strong a word, that's the 5%, but I've never increased the aggressiveness on a tuning loop. Typically, it's always pulling back on those numbers on it. Bobby, you got some of that, some on that as well?
Yeah, I mean, it's always about those kind of long-term consequences, and going back to the tuning idea, it's always oh, we want to get there as quick as possible and fast, fast, fast. And that may solve your short-term problem, but it's going to cause much more issues in the long term, right? If you increase the feed rate to a reactor, right, you may solve that short-term production bottleneck, but in the long term, now you've got faster catalyst deactivation and increased wear and tear. And you kind of always have to balance the cause and effect of everything that you do, right? Just because you can do something doesn't mean that you should do something. And so this consider is kind of a way to take a step back and ask yourself, yes, these are all great things that we've done. We've identified it, we've anticipated it, we can see the big picture, it works. Okay, now, does it actually make our lives easier, or is it going to cause problems down the road, right? And you have to do this with almost every decision you make, not only in process control and automation and optimization and programming, just in life in general. You always have to look at the short and the long-term consequences of everything. And if you don't take a step back and just ask yourself, does this actually make things better in the long term? We're going to miss out on stuff, right? And so, that kind of takes us to the last section, which is to recognize, right? All of this is starting to build a process, right? Recognize is you start to learn what's going on. You start to apply that understanding to identify the actions, right? All of this is a process to get to the end of the end idea of let me recognize what the solution is. Having a deep understanding of a system structure and a function enables them to identify and evaluate those actions, right? If you've identified a heat exchanger as a bottleneck in the process, you have to recognize several possible actions to be able to correct that. Weigh the impact and the benefit, the consequences of this. Is it going to cause more improvement, right? What is the action, right? Recognize is the end where you say, look, this is what we actually have to do, right? This is the process, right? It's recognizing the overall kind of goal and end game. It's defining what the solution is, because now you've taken into account all of those systems, right? So, Vince, from, kind of the development standpoint, how do you, use this recognize to kind of finalize the product features and designs?
Yeah, so I mean, this is the final step is understanding, okay, all of these pieces of a system, and in my case of software, actually comes together to deliver whatever functionality it's supposed to deliver. Being able to recognize that, okay, the quick fix probably isn't the easiest, or sorry, isn't the most suitable solution, because while in the short term it could, we can release the fix to the customer so that they're happy. Down the road, we can have more problems just in terms of technical debt, right? If you keep band-aiding and patching small fixes, eventually it'll just be, an uncontrollable a mess that you have to sort of maintain. So recognizing that, okay, just because I can and do this quick hot fix doesn't mean that that's the right way. Let's architecture the software so that it's more robust, so that down the line we could make small changes rather than having to redo the entire code base again. We actually ran into this about 7 or 8 years ago, where we put all of our eggs into one technology stack. I don't know if any of you guys know about Microsoft Silverlight, but that was the technology that we were sort of behind, that we put our development effort behind, and it turns out that it wasn't robust. It wasn't uh, the longevity wasn't there. Microsoft actually dropped support for it back in like 2014 or 2015. But when we developed Plant ESP, that was the technology stack that we went with. And we sort of had to shift our gears. We had to re-architecture and rewrite the entire software again, using more modern web frameworks, and eventually using HTML5 as our front end technology, and using JavaScript to sort of handle all of the UIs and the button clicks and whatnot. But just re-architecting the whole system, had we recognized that, okay, this is not the technology stack that it's going to be very future-proof, we would have saved ourselves the headache of having to rewrite the entire software.
It's so true, Vince, that you say that about recognizing the backward float. There's another recognize going forward out of it as well, out of a process. Again, I'm coming from the process point of view. The recognizing that's future proofing it. We can future proof in a process by going, okay, so what does this new mode of operation mean for us? Do we have opportunities elsewhere to make a higher quality product because we can run tighter to a specification? We can be in a much better chemical conversion zone so that we make better quality a product. That we're tempering our chocolate perfectly at the ideal temperature, so our customer has a lovely snap in their chocolate when they get it. Rather than a broader range, there is that opportunity with all of this background data that you've built up from examine, anticipate, envisage, validation, consider. You then can go, so are we done? Or is there an opportunity here to circle back around, or at least to take this more stable, more consistent process and improve it again? It's the beauty I find is that you've already opened all those conversations. You've talked to operations, you've got their trust, you've developed a relationship with the process people who actually make the product, you know, and they go, you know, if only we could, during the discussion, if only we could, when you get to the end of that system could change, you can then give this feedback and go, I think we can now if we, you know, you've opened that conversation. It's the beauty of our software is that it allows those conversations to happen within the whole group. We're conscious of time, so I'm going to wrap up that bit of it there now. We have 2 more slides that I'm just going to work through just to kind of bundle all of that in together. This interesting that this conversation has gone over what we had planned, because there's an awful lot of information in these 3 heads. You know, that there's a small pat on the back for that one, but it's, you know, it's such an interesting topic that you can get lost in the forest, you know, and not see the trees. But you do have to remember to lovely picture there of be above everything. You may be concerned with, to continue the analogy, a branch in the tree in that forest, but you do need to step back. The beauty though is when you do step back from that and you see where the architecture or the structure you've come through, you actually end up in a very powerful position. From a visual point of view, you can see the big picture, the full thing, but you know the nuances of that process, which then allows you to take that step to the next phase. It's really the key to that is those interrelationships between those groups and understanding that process. You get that from the data. You get that from the analytics, from the data lake, from Plant ESP watching your loops, but you also get it from the historian and the data from the maintenance logs and all of that pieces of information that pull in together. The system thinkers, whether we know it or not, anybody that operates in a process manufacturing environment is a system thinker. It's there. It's just structuring it so that you can organize it and bring it in. The next slide there, Bob, just we'll just to close out on it. It's this, I suppose, 5-step process, 6-step process, that our 4-step process here we see. It's that examine, anticipate, envision, validate, and consider. You're looking at each piece of that. The more information you can feed into that, the more questions you can answer, the more questions you can validate, the stronger the information. You know, good data in, good information out. Stupid in, stupid out. If you don't classify the data coming in and validate it in its individual components to support it, is really what it is. You know, that, because those relationships are complex, particularly when you're talking about an air handler on the roof on a building that's a kilometer away from the utilities building, and the department in the utilities building don't talk to the department and the air handling systems. You know, they're not aware of those interrelationships. There's many of those that I could talk about from systems that, you know, one system was being controlled at a very fast time constant because they could, but it was actually messing up a totally other system on the other side of the plant. So I'll just leave you with that one. Just because you can doesn't mean you should with process control. The slower, the softer, the more respectful, the more stable your processes will be. Michelle, I think we're going over to you for the next section.
Yes, gentlemen, thank you. That was amazing. 3 different perspectives. Like you said, a lot of brains between the 3. It was fantastic. So with that, if you go to the questions box, I mean, seriously, you have experts here. Type in your questions. I know we're running a little close on time. We are willing to stay late to, you know, answer your questions by all means. So don't worry about that. In the meantime, while you're typing in your questions in the questions box, can we have the next slide, please? You can also whip out your phones, snap a picture of the QR code that will take you right to our website. You will find industry-specific articles, case studies, white papers, sign up for training sessions. It's all there for you to review, read, enjoy. All right, if we go to the next slide, I will pull up a poll in a second while you continue to write down your questions. I have one here. Of the 6 aspects or habits of system thinking, which one do you believe is the most important? I'll let one of you feel that.
That's a loaded question right there. I think you're going to get 6 different answers. For me, it's there's a tie, right? And I know that's kind of a silly answer, but examine and envision to me are really critical. You need to identify those kind of individual points, and you have to be able to take that step back and envision the bigger picture, right? You need to see you need to see the whole forest, right? You can't just look at the one leaf, to kind of go back to that analogy. And so that envision is critical, but you have to understand where that one leaf kind of fits into to the forest, right? And so examine and vision are kind of the two that I'm always obsessed with on my kind of process for doing analysis and optimization and so forth.
I would go with consider, but the presumption would be envision is robust. It's the stupid in, stupid out. Good data in, good decisions out. It's so important to spend the time in those earlier phases. But the consider is where you actually then have to go, okay, so what are we going to do with this information? We wanted this system to control in 15 minutes. It's never going to do that. So we need to change our process approach that it will maintain in 30 minutes, or et cetera, et cetera. There is the consider is going to bundle all of that information together and start to make good decisions with that information.
Yeah, it's
Vince?
funny because for me, sorry, let me just jump in real quick. Validate
Sure.
is the one I would go with, and I'm a software guy, so good data in, good data out. You have to make sure that if the right value comes in, the right value should also come out. And if it doesn't, then there's something wrong with the way that you've designed or architected the system.
So, attendee who asked that question, that's a bit of a fudge. But coming from the 3 sectors of industry where we are, it's very understandable.
All right, I have a poll up. Please have someone from control station provide me with more information. Just information about fast, quick tuning software, control loop performance issues, maybe a 90-day plant eval, hands-on training, a life cycle action plan. I'll leave that open while we take the next question. What are the predictive methods, if there's any, to envision the process parameters?
That's an interesting, that question has a lot of different answers depending on what direction you take it from, right? There are a lot of really interesting predictive methods, whether it's machine learning, AI engines, or even just kind of direct model-based kind of approaches, traditional optimization approaches, right? And it really comes down to is, what are the process parameters you're after, and what is it you're trying to envision? If you're trying to, maximize production out of a crude unit, right, you're going to have very tangible values that you're trying to drive towards. If you're trying to predict things like utility costs based off of historical data to try to say, what's going on, right? It really depends. Like those, some of the machine learning and AI stuff is pretty good at things that are repeatable. I have kind of an odd background in machine learning and AI just from graduate school, and the precision or accuracy of them, and obviously those are two different things, depend on your training set. For me, I have always found that machine learning and AI engines are really good at interpolating within the data set. So if the conditions that you're trying to predict, the conditions that you're trying to envision or drive you towards have existed in the past, those models work really well. If there is an event or a condition that has occurred that is completely outside the realm of anything that's ever happened before, these models aren't going to be able to predict it because it's never happened before. They can predict what's happened again, right? But they can't necessarily create a new event. They can tell you that, hey, the behavior is now driving outside the bounds of what is normal. Somebody do something, right? And that's also a very valuable thing, right? If you've got a dryer that's suddenly operating in a condition that the models have never seen before, that in and of itself is incredibly useful information to be able to drive events. And you know, these models are powerful, but I'll also argue they're only as good as the people who use them, right? Just throwing an AI model on something and expecting it to work out of the box is wishful thinking, right? You really do have to have some experts, some data scientists, and process understanding to really kind of build that thing around, build that model around those known conditions.
I suppose what we do with the models with the software is, you know, it's to understand your process. Like our system thinking, the model will explain what the process is doing. The accuracy of the model will give you the degree of security and certainty as to the decisions you make with it. You know, if the time constant in the process is 15.2 minutes, accuracy there is not going to critically hurt you at 3%, a 5% accuracy. A model that is 30 seconds, then your accuracy may have a more a tighter requirement, I suppose. So, you know, how do we envisage? Well, it depends on the model, I suppose, but getting that model first and understanding is key to the good decisions that come out the back of it.
Yeah, and I'll just add that this is really where your domain experts would be brought in. Just from a software perspective, I rely on Bob and the services team a lot because they're out in the field, they're delivering, they're looking at the PID values, and they just have that domain knowledge of how, you know, the physical aspects of a plant work that me, being from the software side, I really don't have. So just, you know, if whoever is in charge of that side of the system, whether it's your instrumentation guy or your process engineer, they know it better than, you know, someone that's coming outside and trying to fix it. So having that domain expert will actually be beneficial in this whole systems approach, just knowing who they are. And yeah, that's just my input.
Okay, hopefully that answers the question. We have one more question. Let's see here, and everyone's hanging on, so everyone's still interested. You mentioned the time constraints of process. Any tips on how to manage them and align them to process optimization?
Yeah, I suppose from the practical side, you know, as I just said, it depends, but you need to start at the outside of your systems and work inwards, you know, and every time you measure a process and you get the model, then bring that model to the next process, just so you're not bringing it to apply it to it, but be respectful of it, is the thing. And just because you can doesn't mean you should. If the time constants, if they're very fast, if in process manufacturing, if your process responds within seconds, it doesn't need to respond. If the time constant is 10 seconds, 20 seconds, why not let that respond in 1 minute? Because in the grander scheme of things, a 1 minute response is light speed in most manufacturing times, you know, so it's well capable to adapt and address. The problem I see with aggressively managed speed controlling processes, they cause oscillations that push down the process. So the slower you are on the outside, the more precise you can be in the core. And unfortunately, we're brought into systems to understand them because there's a problem in the core, but that's actually, it's the poor PID in that core is struggling with all of this variation from aggressiveness to oscillation coming into it. So time constants as slow as possible is what I would say, to be to build your stability, to reduce your aggressiveness, to lengthen your controller time constant, so that it's being very adaptable, but again respectful of the process is what I would say. Bob, I see a nod.
Yeah, I mean, it's that just goes to my philosophy when doing optimization is every loop needs to be tuned as slow as the process conditions allow it to be, never faster, right? You treat everything as how slow can I make this? And you know, the answer is sometimes you can't make it slow because it's a boiler drum level and it needs to respond quick, or this is a safety system or something. But you should always kind of have, you know, in your kind of outline of the process, well, how fast does this really need to be, right? And then try to go as slow as the process conditions allow it to be, never faster, and you're always going to be in good shape, right? If you can take 5 minutes to get there and it doesn't impact anything, take all 5 minutes, right? It's you know, driving a car with a bowl of chili on your lap, right? Yeah, you could drive really fast, but odds are you're going to make a mess and it's not worth the speed, right? Take your time, let the process get there, and respond, you know, as fast as the conditions, you know, never faster than it's needed. So yeah, agreed. All right.
All right. Do you want to go to the next slide? If you should have further questions, please feel free to contact Damien himself. I have his email address there, as well as Kathy Sweet. They handle, like I said, EU, Middle East, and North Africa. In North America, we have Brian Coughlin and Alessia Testani. So thank you everyone for continuing to hang out with us today. I'm sorry we ran a little bit over, but it was great information. We appreciate it. Bob, Damien, Vince, you guys rock. It was great. Thank you.
Excellent.
Thank you.
Thanks everyone.
Bye-bye.
Bye.